keypad is a 3 by 3 grid with the digits 1 to 3 in order on the top row. So 1, 2, 3, then 4 to 6 in the next row, 4, 5, 6, and 7, 8, 9 in the bottom row. Seb has the keyboard upside down, so rotated through 180 degrees, and types his 3-digit PIN as if the keyboard pad was the right way up. Okay, so if I rotate it, the 9 is now going to be top left, and it's going to be 8, 7. 5 is going to stay where it is, but this is going to become 6, 4. And then at the bottom, we're going to get 1, 2, 3. I mean, you can turn your head or turn a piece of paper if you don't have paper to be able to see this. Now, the number he types in turns out to be k times his original pin, where k is a positive integer. Find all possible pins and prove that there are no others. So let's say if his pin is A, B, C, where this is written as a 3-digit integer number, actually question 1 uses the same notation, then what does he actually type? This is when you have to sort of try and get a relationship between the left-hand side and the right-hand side. And what you actually see, it takes a bit of time maybe, but they add to 10. 1 plus 9 is 10, 2 plus 8 is 10. The pairs add to 10. So if he typed, if his pin was a 2, he would have typed in 8, which is 10 or 2 less than 10. So he would type in 10 minus A, 10 minus B, 10 minus C as his pin. So I want to go from this into kind of powers of 10 form. So like 23 is actually 20 plus 3. Okay, so his number, so he types, the number he types is therefore going to be 100 times 10 minus A. Because if his pin was a 3 and he typed a 7, that would actually represent 700, because that's the first digit. Plus 10 times 10 minus B plus 10 minus C. And that is then going to equal K times 100A plus 10B plus C. We've got ourselves an equation to solve. So we're going to consider different values of K, but first of all, let's just play around with this. Let's multiply it out. I'm going to get 1,000 minus 100A plus 100 minus 10B plus 10 minus C equals K. And that leaves me with 1,110 minus 100A plus 10B plus C. In fact, what I can then do is add it onto both sides, that 100A plus 10B plus C, and I'll do it in steps. And actually then factorize that out. So I'm going to get K plus 1 times 100A plus 10B plus C. Now, when I got to this point in the question, I actually started putting values of K in, which is absolutely fine. You can do it that way. You can systematically work your way down from K equals 9, because it can't be bigger than 9, down to 1. Um, but there is actually a quicker way to do it. And I did realize it after a little while because we know that um, we know that k plus 1 must divide into 1110 actually. So let's find the prime factorization of 1110. Well, it's going to be 111 times 10. 111 is then actually divisible by 3 because the digit sum is 3. Actually 3 times 37. Here we get 2 times 5. So it's 2 times 3 times 5 times 37. And therefore, k plus 1 can only take values. Well, it can't equal 1 because then k would be 0, but it could take values 2, 3. It can't equal 4 because 4 won't then divide into 1110, but it could take the value of 5. Could take 2 times 3, 6. Okay, that 6 divides into 1110, or 10. And that means k can only take values. Now I just need to minus 1 from each of them. 1, 2, 4, 5, or 9. So let's take a look at each of these cases separately. K equal to 1, or k plus 1 would then equal 2. There's a couple of ways you can do this. One way you could do it would be to sub in 1110 equals 2 times 100a plus 10b plus c. So that'll give me 200a plus 20b plus 2c. And then figure out a, b, and c from here, remembering that they are single digits. So a must equal 5 to get us up to 1000. 6 would be too much. You can't have b as negative. Then we'd be left with 110, so b would have to equal 5 to get the 100 from that. And c would equal 5, which would give us 555. This is quite a slow process though, and actually not necessary. Instead, we can just let x equal our 100a plus 10b plus c. Remember, that's our original pin number. So our equation is then going to be 1110 equals k plus 1 times x. So that means that x is just going to be 1110 divided by k plus 1. That's going to be so much faster to get all of the different pins. Because, for example, k equal to 2, x is going to be 1110 over 2, which gives us 555. So I'm going to use this approach for all the rest of them. Okay, let's just keep in mind we've got 1, 2, 4, 5, and 9. Let's go with k equals 2. So x is going to be 1110 divided by 3. Which gives us 370. But I have to reject that one because there is no 0 on the keypad. Okay, next up, we've got 4. To divide by 5, we can divide by 10 to give 111 and times by 2. 222, which is okay. K equal to 5, which takes us back to k plus 1 equaling 6. Now we've already divided by 3, so you can just take the 370 and divide that by 2, 185, which is okay as well. So 1, 2, 4, and 5, that just leaves us with 9. gives us 111. And these four are the only pins. Five, 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 222, 111. Sorry, I haven't written them in order, but it's okay. 185. We've rejected the 370. That's, we've done enough evidence along the way. We've said we don't need to check any other value of k. We've shown that k plus 1 had to take these specific values. And then we looked at them turn by turn, got the four answers, explained why 370 couldn't work. That is our complete solution.